for the conference. So our first speaker will be Frank Vanden Bosch, who'll be using satellite kinematics to constrain cosmology and the galaxy-halo relations.
All right, thank you. Okay, so I'm going to talk about a new project based on using satellite kinematics to look into the galaxy-halo connection, and in particular also to do cosmology. Now, Tuesday, Johannes told us that when you combine galaxy clustering and galaxy-galaxy lensing, and you do halo-occupation modeling to marginalize over uncertainties in galaxy formation, and thus constrain cosmological parameters, then you find some tension. And that tension is shown here in three different renditions. This is from 2013 when my student Marcello Cacciato did this analysis, and he found these blue constraints here on omega matter and sigma 8. Back then there was in good agreement with WMAP, but then Planck came out and you see a clear tension. 6 years later, Johannes analyzed the Bosch data, and just like Alexei 2 years earlier, finds its tension very similar. In fact, even the DES, the Dark Energy Survey's first-year data release analysis, comes up with these blue contours compared to Planck. And it's this consistent tension that the low redshift data prefers a lower value for sigma 8 and or a lower value for omega matter. Now, in principle, this could be very exciting. What we could be seeing is new physics beyond the vanilla 6-parameter lambda CDM cosmology. We might be seeing evidence for non-zero neutrino mass or for a running spectral index. But before you write that Nature paper, making a fool of yourself, you better check this, that this is not systematic errors. Okay? And we heard from Johannes that there's various things that bother us and that worry us. Assembly bias, the impact of baryons. And we sort of have to really get our act together and deal with these issues if we want to be able to do something along these lines. Another approach is to try and see if we can use some additional or complementary data. And such data is available in the form of satellite kinematics. Now, the beautiful thing with satellite kinematics is you don't need anything additional to what you already have. If you have a redshift survey, you have all the data that you need in order to do satellite kinematics. Okay? Satellite kinematics, unlike, for example, galaxy-galaxy lensing, where you have to measure these little shape distortions and points with function corrections, is a really tricky measurement. Satellite kinematics is independent of halo assembly bias. It doesn't depend on the clustering of the halos. Okay? But for some reason, quite mysteriously, it has been heavily underutilized. To the best of my knowledge, there are only 2 studies to date that have analyzed satellite kinematics in the context of a full galaxy-halo connection picture. And incidentally, those 2 students were both my graduate students, Surut Moore in 2009 and then Johannes Lang in 2019. So how does this work, satellite kinematics? It's very easy, right? The satellite kinematics just means you're trying to use the motion of satellite galaxies to probe the depth of the potential well. Okay? So the way you do this is you first have your redshift survey and you have to put a cylinder around galaxies to identify centrals and satellites. They don't come labeled as such, unfortunately. So typically you put a cylinder around each galaxy, okay, certain depth in redshift space, certain aperture. And if you are the brightest galaxy inside that cylinder, you are a potential candidate to be a central. Okay, you're called a primary. And then fainter galaxies in that cylinder or in a similar cylinder around that, they're called the secondaries or the satellites. And for each central satellite pair thus identified, you can then measure the velocity difference along the line of sight from the redshifts. And you can plot that as a function of the luminosity of the primary or the central. And you see a nice trumpet-shaped figure. These are all the real satellites. These are interlopers. You have to correct for that, but it's quite easy. You can see by eye basically where they are. Okay? And what typically people then do is you say, okay, let's now take a bin in luminosity. Okay? You sort of stack all centrals of a given luminosity bin, plot the PDF of the velocities, and you measure the width of that thing. Okay? That's the satellite velocity dispersion. And if you do that, you can plot that as a function of luminosity, and you see satellite galaxies move faster around brighter galaxies, aka they live in more massive halos. Okay? Makes all sense. And then the final step is now you want to model this with, say, a galaxy halo connection model, and okay, put your constraints. Now, this has been done in detail by all these other people. The latest study was part of Johannes' thesis, 2 papers that appeared this year. And basically what we show there is we improve the analysis that was done by Surut 10 years earlier. There was quite a bit of room for improvement, it turned out. And Johannes was able to come up with constraints that are very competitive with and in very good agreement with other constraints from both lensing or clustering. Okay? So the take-home message from all of that is basically that we now have this additional method which really has been matured into a competitive complementary probe of the galaxy halo connection. So what's next? So what's next is Basilisk. Basilisk is a perfectly legitimate acronym for Bayesian hierarchical inference with satellite kinematics. And it's satellite kinematics on steroids, and it has a number of advantages. What, for example, the method that Johannes and the student have used does is it basically can only be applied to a volume-limited survey. Okay? That means you start with your Sloan digital sky survey, and you only use the data here in this little rectangle. Okay? So you throw away a lot of data. Basilisk can be applied to all data from a flux-limited survey. So in the case of Sloan, we go from about 6,500 to about 43,000 satellites. So it's a dramatic increase in the amount of data, which is always a good thing. The most important thing is that what you do in the standard method is you use a summary statistic called the satellite velocity dispersion. That means you throw away a lot of information. You know, you have an entire PDF of velocities, which you ignore. You just measure the second moment. Okay? You don't use a projected separation of the satellites. There's additional information there. You can probe the radial profile and the anisotropy. Okay? So what we do instead in Basilisk is for each central satellite pair, you have two numbers. You have the line of sight velocity difference, delta V, and you have the projected separation, RP, and you just ask, what is the likelihood for all that data in its raw form given a model? Okay? And that model is basically a conditional luminosity function model. In addition, if you run these isolation criteria, right, you put your cylinder on the galaxy, and you have identified now a primary, for every case that you basically get now a satellite, there's about 9 centrals for which you find 0 satellites. So for those, you don't have a measurement of delta V because there's no satellite. So you normally ignore that. But if you actually plot the probability that a primary of this luminosity at a given redshift has 0 secondaries, and there's information there. There's information about how many satellites are there in a given halo. Why should you throw it away? Basilisk uses all that information as well. Okay, so the way it works in detail is a bit complicated. It's a Bayesian hierarchical inference scheme. It accounts simultaneously for the scatter and the galaxy halo mass connection, for orbital anisotropy, fiber collisions in Sloan, interlopers, and basically the crux is to compute this likelihood. And the way you do that is you say, okay, given a luminosity of the central and its redshift and its numbers of secondaries, I can compute a probability that it lives in a particular halo mass. You integrate over all these probabilities, you marginalize over halo mass. That makes it basically the latent variable in this hierarchical scheme. And then once I know the halo mass, you can calculate, given a halo mass, what is the probability that the satellite has a certain delta V at a given projected separation along the line of sight. Right, so the nice thing is, this is basically where your halo occupation modeling goes in. Okay, my conditional luminosity function, from that I can compute this. And your dynamical model basically is the other part. Okay, and for that we just use the spherical genes equation. Now, this is the reason why people get worried about satellite kinematics. Spherical genes equation, hold on. That means you're assuming that it's a static dynamical tracer. But we know that satellite galaxies sort of sink to the center and then they merge and new satellite galaxies come in. It's not really a static tracer. Then again, the time scale on which you have that sort of evolution is longer than or comparable to the dynamical time of the halo. So it should be close to a static tracer population. So the upshot is, this is not guaranteed to hold, and what you have to do is you have to test your method in great detail, and that's what we have done. We have made detailed mock catalogs. You take a numerical simulation, you put galaxies in according to some prescription, you put a fake observer in it, make a fake Sloan digital sky survey, apply fiber collisions, put your cylinders on, select primaries and secondaries, and analyze it in exactly the same way as the data. The galaxies are now put in subhalos, so they inherit the dynamics of the subhalos. Okay? I'm not assuming in the model that it's a genes equation. I assume that satellite galaxies have the dynamics of subhalos in the simulations. And you do that, and then you run Basilisk, and it works as a dime. So focus on these two panels here. This is the luminosity of the central as function of halo mass. The gray dots is the actual data. You see there's quite a substantial amount of scatter in the relation. Okay? But this is a realistic amount of scatter, about 0.2 DEX. The red dots are just sampling at different halo masses, the true relation between luminosity and halo mass. Okay? That's a model that I used to make my mock. The blue contours at 95% confidence intervals, okay, inferred by Basilisk from the kinematics, satellite kinematics. So this works really well. Not only that, I can now take 3 cross-section here at different luminosities and plot the PDF of the halo masses, a cumulative distribution of halo masses. So that sort of maps out the scatter in the galaxy halo connection. Again, the circles are the true input. The contours here are the 95% confidence intervals. So not only can Basilisk recover the average relation between light and mass, it can recover the full PDF, including the scatter, okay, with amazing accuracy. It can recover the interloper fractions, it models over that, it recovers the anisotropy that I put in of the subhalos. So all of that works really well. So now that we have tested it, we're ready to apply it to the data. So this is now 43,000 central satellite pairs from Sloan Digital Sky Survey. You see by eye, that brighter galaxies leave more massive halos. You can see individual clusters here sticking out. Here are the projected separations, and here are these probabilities that a given galaxy primary of this luminosity has 0 satellites, right? And that probability gets larger if you go to, gets smaller if you go to brighter galaxies. It makes all sense. This just comes from the flux limit of your Sloan survey. All right. So then you run Basilisk over this data, and you basically get extremely tight constraints. So this is again the luminosity of the central as function of halo mass. I'm comparing it here to 3 previous studies. So there's a purple symbol, that's by Marcello Cacciato's analysis of lensing and clustering. Then there is Yang et al. This is from the Galaxy Group Catalog. Okay, so what you there do is you just take groups with an assigned mass in a particular bin and look at the luminosity function of all those galaxies. That's the conditional luminosity function. And the orange one is Johannes's last year's analysis of satellite kinematics. They all agree, and Basilisk also nicely agrees with that with extremely tight error bars. We fit the luminosity function. Here you can see that we can actually very accurately reproduce these probabilities to have 0 secondaries. So here are 3 inferences that are sort of interesting to look at. I'm going to focus on these 2 actually. So this is the scatter, sigma log L, at given halo mass. Okay? Now most studies in the past have just assumed that that's a constant, independent of halo mass. For example, in Marcello Cacciato, we kept it fixed, and we then inferred an average scatter of about 0.15 dex. In Yang et al., you can directly measure it off from the Galaxy Group Catalog, and at the massive end that agrees nicely. At the low mass end, it goes down. But it's an entire artifact because the masses in the group catalog are coming from the total luminosity of the group members. So by definition, you go to 0 scatter by the time you have 1 group member. So that's an artifact. We know that. Now, I think Johannes was one of the first to actually consider a model in which you give some extra freedom. You say, let's assume a power law dependence here. Okay? So Johannes analyzed the satellite kinematics using a power law dependence, and these are the results he obtained. Okay? So he found significant evidence that the scatter is smaller at lower mass halos. In Basilisk here, I've done something similar, but I used 2 anchoring points rather than a power law slope for no obvious reasons.
Scatter bigger?
The scatter gets larger if you go to smaller halo masses. That's, if I said the opposite, then bad boy. All right, and here, this is now the slope of the faint, this is the faint end slope of the satellite luminosity function. The satellite luminosity function is modeled as a Schechter function, it has a faint end slope, and most of the time we again assume just a fixed value therefore. So both Johannes, for example, and Marcello did that, and they found basically minus 1.2-ish, okay? But in Yang et al., we can just read it off from the Galaxy Group Catalog. And there we found evidence that at the massive end, it sort of becomes steeper. Okay? The satellite luminosity function, becomes steeper. So motivated by that, I decided in Basilisk to also include that degree of freedom. And indeed, the inference is, indeed, the model really likes to have a model like this. Much more so. I'll show you in a minute. Okay? It really prefers a model with a mass dependence so that the faint end slope gets steeper if you go to more massive halos. Okay. So this is all good. Now the interesting part. Now let's do cosmology. Let's combine satellite kinematics with galaxy clustering. So here's a full set of data that we're going to use, combined with projected correlation functions. Okay. Now the problem with Basilisk is I can't just add cosmology as free parameters and marginalize over everything. The reason is I need to sort of keep cosmology fixed, and then I can pre-compute 100,000 things, and then that's the only way this is feasible, because I need to compute a likelihood for 43,000 pairs, and each likelihood is a 6-dimensional integral or something. So But what I can do is I can just run Basilisk for n different cosmologies. And then cosmologies that I pick are cosmologies that basically move along a line of S8, which is this combination of sigma 8 and omega matter. So here's the Planck cosmology. These colored dots here, those are previous constraints from Alexei, from Johannes, from Whitking had a very nice paper just a few weeks ago. And so I'm moving along this line, okay? So, this is, ready for the results? Okay, so here are the results. So this is this S8 parameter. These are the Planck constraints. And these are the constraints from for example, Johannes, but the constraints from Cacciato, Whitking, they're very similar here. And these are the constraints we get. So again, we see the same tension. The model clearly prefers a lower S8. In fact, if you look at the minimum, the delta chi-squared is 21. Now, I basically only have 1 degree of freedom, S8, because I'm marginalizing over everything else. So in principle, this is extremely significant. I'm not sure I believe the significant levels. But okay, this is what I get. You can now even test what do my individual chi-squares look like for the individual things, for the satellite kinematics, for the luminosity function, for matching these isolated primaries, for the clustering. And you see that the satellite kinematics really likes low S8, as does the clustering. The isolated primaries prefers a little bit the opposite, and the luminosity function doesn't really care. Okay? So this is all good. If I now just...
What does isolated primaries mean?
That's this probability that a primary at a given redshift at a given luminosity has 0 secondaries, right? That's also unfitting, and I have a chi-squared for that as well. So here are the results. If I take this at face value, I've inferred that S8 is about 0.77 plus or minus 0.2, clearly in tension with Planck, and a reasonable agreement with, for example, Johannes' analysis from a completely different data set using lensing and clustering. But what I didn't tell you, let's go back one step. What I didn't tell you here, what I did, is I used this sort of standard conditional luminosity function where I keep the faint end slope fixed. It doesn't depend on halo mass. So now all I do is I add that 1 degree of freedom. Now the faint end slope is allowed to vary with halo mass. And what I get, oh bugger. Sorry. What I get is this. So the chi-square drops by 400. I added 1 stupid degree of freedom. And not only that, if I now, it's hard to see here, so if I now renormalize it at the Planck cosmology, my problem has gone away. My cosmological tension is gone. It's basically consistent with Planck. 1 extra weird degree of freedom, and this happens. So this is 1 week old. I'm still, can't sleep over it, but basically.
P0 also agrees?
P0, a lot of this comes from P0 improvement. P0 loves this. Yep. So, conclusions. Satellite kinematics has matured into a complementary and competitive probe. I hope you're all convinced. Okay. Basilisk simultaneously solves for halo mass and anisotropy while accounting for scatter, interlopers, and fiber collisions. For those of you interested in anisotropy, the anisotropy is very close to 0 that I infer from SDSS. Slight radial anisotropy, but it's very mild. There is strong evidence that the scatter in the galaxy halo mass connection increases towards the low mass end, and that the faint end slope gets steeper towards the massive end. And the preliminary analysis suggests that I can reproduce the tension, but that it vanishes when I add that 1 extra degree of freedom that I still don't understand. Thank you. Sorry?
The definition of SA. Show the definition of SA.
Sigma 8 times omega matter divided by 0.3 to the half.
It's a standard thing.
Can I show it? I have to.
And it's standard. Everybody uses it.
This is a parameter that sets things like, that's sort of how the mass, halo mass function changes, the degeneracy in the halo mass function.
Is there any other physical motivation or evidence for a mass-dependent faint end slope?
Yes. You look at high redshift. And high redshift, as you know, the luminosity function is steeper than at lower redshift.
Steeper, but it doesn't vary with mass.
It doesn't?
It doesn't vary with mass. It's just steeper.
No, it's steeper there, the overall luminosity function. So massive halos.
But wait, hold on there.
Massive halos.
It's only
you
for
have-
the star-forming galaxies, but that is also true in the intermediate redshift universe. If you look at the luminosity function of star-forming galaxies, it's systematically steeper than the mix at
Right,
large.
right. All I'm saying is, in massive halos like clusters today, they probably had progenitors forming earlier than lower mass halos. And if there is evolution in the steepness of the luminosity function with redshift, that would be a natural explanation for the steepening with halo mass. So that's.
So if your new result that you're still thinking about holds and you've done away with most of the tension by that one small fix, do we infer from that that all the tension that has been talked about is just due to something wrong with the lensing?
Right. So the fact that all these different studies have found the same, no, there's nothing wrong with the lensing. What is wrong is that we have used a halocapation modeling that is too restrictive. We should use our imagination, right? Every H2D model is the same. Since we started this game back in 2000, everyone is using a 6 parameter model. No one has ever varied this. People have considered very little variation in the CLF either as well. So I think that may be the problem. We've just been too restrictive, and we all agree because we always use the same H2D models.
I noticed that you keep on using luminosities, and yet luminosities are not
Yes,
really
because
mass.
those are observable.
No, just wait a minute. But galaxies of different colors within that will also give you resultant changes in the slopes. So I would assume that if you go
Yes.
back to mass, you may find maybe a different relationship versus mass, and might reduce your scatter. Your scatter is bound to be large because,
Yes,
given L could be a smaller galaxy, bigger galaxy, depending on its color. So you have to naturally
So
increase
Johanna's
scatter.
analysis of satellite kinematics, he did it separately for red and blue galaxies, and we see interesting trends. You basically infer that red galaxies live in more massive halos and blue galaxies, that's all consistent. I hear what you're saying, I completely agree. I mean, in Basilisk, the problem is, you have to take account of the flux limit of your survey. With luminosity, I know exactly what that is. With stellar mass, I don't have to, but it can be done. I've worked it out. Exactly.
Frank, this is fantastic. Only you could do something like this. This is just amazing. However,
there was a but, I knew it.
yeah, but you said it yourself. When you introduce one more parameter and you get a chi-squared improvement of 400, I'm just picking up on what you just said. We've got to be imaginative. How many more parameters are hidden in there? So don't necessarily believe that any problem has been solved.
No, neither do I.
I think rather maybe what you have shown is that this kind of analysis is extremely sensitive to hidden assumptions.
I couldn't agree more with you, right? Radial profile of the rate.
In which case it is not matured.
All right.
We'll do one more quick question while Eric sets up.
Frank, if you're getting changes in the low mass, the faint end slope, one thing that sort of is a concern for me maybe is the selection function of the survey, because you're also you're very ambitious in trying to use all the data. And to me, if you're seeing big impacts in the faint end slope, that also means that you've got to be really careful about modeling that selection function. And yeah, that's just wanted to throw that out. Like that's really hard to do properly.
I thought carefully about this. We take all of that is done in the modeling, so we carefully take all of that into account, as far as I know. And again, in the mock, we've tested it, and it works remarkably well.
But like you need the spectroscopy, and that might depend, like whether you can actually get a redshift might depend on the galaxy type, which might have different radial profiles. Anyway, does the result still hold if you work in a more mass complete sample as opposed to the full sample with the selection effects?
To be determined, but yeah.
Okay, let's thank Frank once more.